It is my pleasure to welcome Darren Croton to Monash to give the talk today. He is a professor of theoretical and computational astrophysics over at Swinburne, where he does a lot of work on large-scale items, so galaxy evolution, in both local and distant universes. So he also is the founder of the Theoretical Astrophysical Observatory, which is an online system that allows you to make a whole bunch of mock catalogs, so people who are working on computer simulations are able to make things similar to what we should see, so we can do some nice comparisons. Hopefully I didn't botch up that explanation too well. But he's been a professor at Swinburne, and now he'll be here to talk to us about black holes. So thank you very much.
So thank you very much. You can all hear me? Yep. Let me know if you can't hear me or if there are any problems. There's nothing worse than talking without communicating. So let me start by asking a question of you guys, because I like to get to know my audience just as much as you like to come and listen to a speaker. So how many people here work at Monash? All right. How many academics do we have? And astronomers? All right. How many? Oh, astronomer, great. How many retirees or? Yep. Great. All right. I love you guys. You guys ask the best questions. All right. My goal here is not to speak to the astronomers, so you guys can leave now if you want. We're done. But to speak to you at a level, hopefully that you'll be able to understand. And I'm really looking here to give you a sense of the wonder and amazement of the universe in which we live. The focus tonight is going to be on supermassive black holes. And for those of you who don't know the difference between a black hole and a supermassive black hole, other than the very impressive bit at the front, I'll go into that. All right. But first, before I start, let me tell you a little bit more about myself. For many people who know me probably don't even know this. My wife, who's in the audience, perhaps doesn't even know this, that I was actually at Monash for 2 years in the late 80s studying music. So for those, especially those retirees, you know, how many of you have children who in their 20s was bumming around doing nothing with their life? Yeah, some hands going up, or very enthusiastic hand went up there. All right, so that was me. All right, so I came to Monash. That's where you go when you don't know what you want to do with your life, I guess. Came to Monash, started studying. Well, it's where you get a sense of purpose. All right, started studying music, played in the band scene and in the pub scene for many years here in Melbourne. Ended up leaving that and traveling around Australia in a four-wheel drive. And by the time I was in my mid-20s, I kind of realized I couldn't do this for the rest of my life. You know, at some point, you've got to stop and build something. The light went on in my parents' eyes. Thank God, he's starting to figure it out. And so I went back to university. And what I decided to go and do was the thing that potentially didn't have a career, because, you know, studying galaxies and black holes, you know, why would anyone pay you to do that? But it was the most interesting thing to me. And so what I'm hoping now to convey is that sense of wonder that I got when I was younger. And I do see a lot of young faces in here, hoping to inspire you, perhaps not to do this kind of research. That's very dark. But all of science, there are amazing things to learn about this world, and this is just one of them, albeit a very extreme thing. So let's begin, okay? So we're going to start simple with general relativity, okay? I just want to set the bar at a nice low level for you guys, okay? After we talk about general relativity, I'm going to take you on to black holes, which naturally follows. I'll show you why. Because we ultimately want to talk about supermassive black holes. They live in the hearts of galaxies. So we'll have to sidestep a little bit. I'll give you a primer on galaxies, okay, what they are, what they look like, some of their general properties. Then we'll move on to the main attraction of the night, supermassive black holes. And if we have time, we'll sidestep into wormholes and talk about some really crazy stuff like time travel and things like that. All right, so in reverse order, we're going to end at wormholes, hopefully, if we make it that far. But star attraction will be supermassive black holes living in galaxies. To get there, we'll have to talk about galaxies. We'll have to talk about black holes themselves. These are the stellar mass black holes. And in order to understand where black holes come from, we'll touch on general relativity. So let's start there now. Let's start with Einstein. A lot of modern physics starts with Einstein. Okay, did everybody bring their pen and paper? Okay. All right, so everybody write this down. You will be tested on this later. So these rather intimidating mathematical equations are called Einstein's field equations. This, in my mind, was the pinnacle of his genius. This is general relativity. Many of the other things that he's known for were areas of physics that were already being worked on. He came and he put the icing on the cake. He took the ball across the line. But general relativity, in many ways, came out of the blue. It wasn't something that people were thinking about. The world at that time was kind of happy with gravity and our understanding of dynamics, how the stars moved, how the planets moved, things like that. There wasn't necessarily a pressing problem or something that needed to be solved. And yet Einstein started to think deeply about these concepts. And the formulation of those concepts mathematically and in the physics that mathematics describes is what we call general relativity. And it really did change the way we look, not just at planets and gravity, but the cosmos as a whole. Okay, so these equations are very intimidating. Don't be intimidated by them. Physicists like to make things as simple as possible, and so we can reduce them down to make them look like this, the field equations. And I'm not expecting you to understand these in any great detail. That's not my goal here, but I just want to highlight 2 points about this equation, which is key. Okay? So there's two sides. You know it's an equation because it has an equals here. Okay? And there's two sides to this equation. And this equation relates two quantities about our world. This was the realization of Einstein. On this side, we have an equation that describes space-time. And by space-time, I mean this world, this universe that we live in, the fabric. Okay? It's a mathematical description that we call ultimately the metric that defines the four-dimensional space-time, 3 spatial dimensions and 1 dimension of time. So that is the left-hand side of Einstein's field equations. So on the right-hand side, he has an equation that describes the content of that space-time. And the content of that space-time is characterized by its mass, or its energy. Many of you will remember that special relativity tells us that E equals mc squared. Okay? And you can see in this equation, c comes into it here as well for general relativity. C is just the speed of light. It's a fixed number. What that basically says is there's an equivalence between E, energy, and m, mass. Okay? So on this side of the equation, this is the matter or energy content of the space-time. And Einstein's genius was that he realized that these could be related. These are related. And he wrote down a mathematical formulation of that relation. So let me show you visually what this looks like, what this relationship looks like. Okay, so here we have our space-time, and we're representing it as a two-dimensional grid here because it's very hard to draw a three-dimensional picture of such things. So we have our two-dimensional space-time, and in this two-dimensional space-time we put, let's say, some planets. Okay, so there's one here. This is a rather large one, a bit smaller, smaller still. And you can see what putting this mass into this space-time does. It curves it. So who knows what we call that curvature? What's another name for that curvature? Gravity. Okay? So Einstein's genius was that he took the curvature of space-time and described how adding mass or energy into that space-time changes that curvature, the changing of which we call gravity. And it has a very particular effect. It bends space-time as we put more mass in. Okay, that's what we call gravity. And that's why general relativity is a theory of gravity. And it replaced the Newtonian theory of gravity, which had been the standard description of gravity up until that point for many hundreds of years. Although general relativity reduces to Newtonian gravity for all the situations that Newtonian gravity accurately describes. So let's have a look at this a bit closer. Okay, so here again I've got a sheet. And this time I'm describing some trajectories in our space-time. Here we have a person, let's say, standing at this point here, and they shine two light rays out, one in either direction. And they will just keep propagating as they move out in that space-time. But if instead we put a mass in its path here, we see the expected result, that curving space-time, which is described by Einstein's field equations. Curving space-time deflects the path. Okay? And that deflection is gravity. Okay? And that's well described by a parabola, for example. So let's say I take my iPhone here, and to the horror of many, I throw it. I throw it in a straight line, but when I let it go, what path will it take? It'll curve down, all right? And it's exactly the same as what's happening with these trajectories here. The curvature of space-time causes the paths of objects to deviate from the direction they would otherwise be going. In this case, we're on Earth. The Earth dominates the dynamics of objects around it because of its gravitational field. And the field equations very accurately describe that behavior in great detail. Okay? So this was a new idea. Before that, things in space and space itself were very separate concepts, and nobody had ever linked them in this way. So any new theory needs to make a prediction, needs to make predictions, needs to be validated. And so general relativity was first validated through what we call gravitational lensing. So let me quickly describe this. It's basically the same idea. You have a source here, let's say this is a star, and the light rays of this source will propagate out. Okay? And this is us over here, where we want to observe that source. But there's a massive object in the way which has a very strong gravitational field. And so this strong gravitational field bends the light rays in such a way that they focus down on us. Okay? So what would we see from this situation? We would actually see two objects because our eyes just trace back along the line of sight. Our eyes can't follow that curvature and bend back to the original object. They just follow along the sight. So we would see where there's actually one object, we would see two. Now let me show you a real-world example of this. This is a gravitational lens called the Hooker lens. It was named after the famous astronomer John Hooker, who sadly died not long ago. What you're looking at here is a fairly massive galaxy in the center, and this is what we would call the foreground object. It's actually relatively close by to our galaxy. Behind that, there's what we call a quasar. Now, we'll go into what quasars are in a little bit, but a quasar is very, very bright, and typically they're very distant. And this one is distant, and it's way behind the galaxy core. And you're seeing those light rays from the quasar propagate to us and bend around the galaxy. Okay? And instead of seeing two sources like we saw here, we see four. Right? So here's the Hooker lens. So it's an example of gravitational lensing in action, just one of many, many verifications of general relativity, and one of many ways which one of many ways that we know that we can have such confidence in this theory that it is actually describing the world around us. Let me show you an even more impressive example. This is a galaxy cluster. So here you're seeing many hundreds of galaxies, all in the same region of space. And so these are the galaxies here. We'll talk a bit more about galaxies in a bit. But can you see these arcs here? So these arcs are actually distant galaxies. Galaxies way, way, way 100 times further away than the galaxy cluster, whose light is coming towards us and then hits the gravitational field of this galaxy cluster and is bent. And because this is not a nice uniform gravitational field here, there are lots of very massive objects irregularly arranged in this cluster. As the light deflects, it doesn't deflect nice and regularly like Hooker's lens does. And so instead of these galaxies appearing as points, they're torn and they're sheared apart. Okay, so it's another example of gravitational lensing in action. Okay, so gravity bends light. And this is very accurately described by Einstein field equations. But here's a question. What happens if you keep putting mass into this point in space? Okay, you're bending. Let's put some more mass in. Bending further. Let's put some more mass in. Let's keep putting mass in until we get to the point where light can no longer escape from that hole. Okay? And we have arrived at our black hole. These are predicted by general relativity and very well described by the mathematics of the field equations. Okay, so let's talk a bit more about black holes. All right, so I'm going to define a black hole as a region of space that nothing, not even light, can escape from. Now, light has a finite speed, but I've already shown you that it can be deflected by the gravitational field because of the curvature of space-time as light propagates through it, in exactly the same way as you hold a beer glass up, you look through it, and you see everything around distorted. The light gets distorted same way. So for a black hole, okay, what's going on here? We can define a few properties of the black hole. We typically characterize, or what you would typically know a black hole as is by its event horizon. So the event horizon is the point in space at which light can no longer escape. So that's where the escape velocity is greater than the speed of light. So for those who don't know, escape velocity, let's take a rocket, okay, and you put some fuel in and you hit go, and it goes off the ground. Now, if you haven't given it enough thrust, enough velocity, it's not going to make it off the planet. If you give it enough, it will make it off the planet. And there's a critical velocity that it needs in order to get away, and that's the escape velocity. So when the gravitational field is so strong that light doesn't have enough velocity to get away, that's what we call the singularity. And so light traveling, say, along this trajectory will still get curved, but might escape. Light traveling along this trajectory won't be able to. And that critical point is what we call the event horizon. So Hawking and others showed us that black holes, even though they're very exotic objects, are actually very simple in the properties that define them. And so really, you can characterize every black hole by its mass, its charge. So black holes can actually have electric charge, and spin. This is through the conservation of angular momentum, which is a very fundamental physical property. All right, so this leads us to the question. Here's a nice mathematical description. It predicts black holes. General relativity predicts other things that turn out to be true. So how would you make a black hole? And it's actually quite simple. All right, just crush a star down to the size of Melbourne. All right. If you can do that, you've made a black hole. Or if you want to make a supermassive black hole, which we'll talk about in a minute, crush a galaxy down to the size of the solar system. Now, the solar system's actually pretty big. That's nowhere near the size of a galaxy. And so what you need to do is pack lots and lots of mass into a small region of space-time. When you do that, you're going to bend, you're going to curve space in such a way that not even light can escape. Now, this first one, crush a star down to the size of a city. So how would you do that? So we can't do that. but nature can. And let me show you one example of this. This is the galaxy, not too far away. It's an amazingly beautiful photograph. It hasn't come out as good on the projector over here, but you can see the core of the galaxy here and these beautiful dust lanes. We'll talk a little bit about dust in a minute. That characterizes the disk of the galaxy. And out in the outskirts here, there's this bright light, and this is a supernova. So this is an exploding star. So stars really, they're just big balls of hydrogen, and you've got nuclear reactions going on. If you took away those nuclear reactions and you just took all this mass, like take the sun, take away the nuclear reactions, all the mass wants to do is just collapse down to the common center. There's so much of it there. But it can't do that because of the reactions going on in the core, which is what we know as the sun shining. Okay? So stars reach this pressure balance where gravity's trying to pull in, force trying to blow it out, reaches an equilibrium point, and they live for many billions of years like that. Okay? At some point, though, some stars, they run out of their fuel, then you get runaway collapse. And when you get runaway collapse, you can take the mass of a star and compress it down to such a small space and produce a black hole. So supernova can do it. There are certain conditions and only certain stars that this can happen with, but let's just to say here that on average 3 times more massive than the sun when they explode late in their life. The conditions for runaway collapse are met, and you can end up with a supernova through this gravitational collapse. Right? Okay. So let's start to get a little bit more curious about our objects here, our black holes. So what's going on? So the event horizon is a natural boundary between the interior and the exterior of the black hole. Okay? So what happens as you, let's say you're feeling a bit adventurous, so you've got your rocket ship that you built with your retirement fund money, okay, and off you go to the nearest black hole, and I'll actually show you where the nearest supermassive black hole is, because we know exactly where it is. I'll show you that in a little bit. So off you go to your nearest black hole, and you start to get close. So what's going to happen to you? So the first thing you're going to notice is these very strong tidal forces. So tidal forces, what are tidal forces? We know what tides are. It's exactly the same thing. Tidal forces are when, for black holes, is when the force of gravity on your feet is much, much stronger than the force of gravity on your head. All right, so what do you think that's going to do to you? Not going to be pleasant, right? I have a picture of that in a minute. All right, so that's one thing that happens. Very large tidal forces. You will not survive. I do not recommend you do this. All right? The other weird thing that happens, and I'm not going to go into this too much, is that special relativity becomes very important. And for an observer watching you do this, so we're all here watching you do this, time, from our perspective, for you, will start to slow down. In the presence of this very strong gravitational field, special relativistic effects become very important. You'll get closer and closer to the event horizon, closer and closer and closer. You'll never actually get there from our point of view. For you, you will just sail straight across in your frame of reference, and this is what special relativity is about. It's a relative. Okay, I won't say too much about that, but as you get closer to the event horizon, observers at a large distance will see you get closer and closer, but they'll see your clock, your time, slow down as you get closer in the presence of this incredibly strong gravitational field. All right, so let's say you crossed over the event horizon. Somehow you survived. You have a magical suit that does it. Okay, so what happens? The gravitational field is so strong, everything just moves radially towards the center. And from a mathematical point of view, according to the field equations, a very bizarre thing happens where time and space exchange roles. Now, if you can explain to me what that means, I'll let you come up here and finish off. Suffice to say that the equations break down at that point, and we don't believe they accurately describe what's actually happening. But it wouldn't be pleasant. So here you are in your special suit, and you're experiencing very large tidal forces. Now, astronomers have a name for this, very scientific name, called spaghettification. And if you go to Google and you Google spaghettification, you will get that. Right? So this is all good and well, right? But I think many of you already know that direct evidence for stellar mass black holes has recently been found. There was a public talk on this not long ago, as far as I understand, and let me just quickly show you that. LIGO is an interferometer. If you don't know what an interferometer is, it's probably the most important experimental apparatus in all of physics. So many of the great discoveries in physics going back a long time have been done with an interferometer. Basically, it's pretty simple. You just shine a light at that point and reflect it back, and you shine a light in that direction and you reflect it back. And as light comes back, it creates what's called an interference pattern. It's like a first-year lab experiment that you'll do. And we use very strong lasers nowadays. And so what LIGO was doing was shining a laser 4 kilometers that way and shining a laser 4 kilometers that way, and looking for waves in the fabric of space-time to go through, gravitational waves. So they were using the math that I showed you that makes predictions for how these waves should propagate. And if the wave comes through this way, then the length of that 4-kilometer path is going to get a tiny bit shorter and a tiny bit larger as the wave goes through. If it comes through that way, same. But the other path won't change. And then the interference pattern will change when the two path lengths are different. And this is essentially what you're seeing here is the wave going through. And LIGO has 2 detectors here. What they worked out through extensive theory and modeling was that this was a merger of 2 roughly 30 times mass of the sun black holes. And this happened about 1.3 billion years ago. So here's a little movie that they've made just to illustrate this. So imagine this is the detector here, and very hard to see. Black holes are black, after all. You see these 2 black holes merging, and as they move through space-time, they're inducing ripples in space-time, and these ripples pass through the detector in a particular way that gives us a very particular pattern. And if you're wondering how the hell can they infer that from this, think of it this way. If I covered your eyes or put a mask over your eyes and brought different animals in and got them to make their animal noise, you'd probably get 10 out of 10 because all animals sound different. All they're doing, every single one of them, is inducing pressure waves which propagate along the space between them and you. You have the sophisticated machinery to distinguish the very small differences in those pressure waves and associate it with an origin, and that's essentially what they've done here. This is one of the most beautiful results I've ever seen. When I knew, everybody knew this announcement was going to happen, and I was expecting a scatter plot of points with a model fit through and then them to make some claim. But it fit the theory so accurately, it was just astounding. There's lots of evidence for black holes, and this is the most recent and the most direct. All right, so we want to go up in scale here, so let's talk about galaxies now. So here's a beautiful picture of a galaxy. This is probably typical of our Milky Way. This is what we would call a spiral galaxy. Let me just give you some general properties to start, though. All right, so how big is a galaxy in terms of mass? Okay, typically about 1 million to 1 trillion times the mass of the sun. 1 million to 1 trillion stars. That's what makes a galaxy. All right, how old are they? About 6 to 12 billion years old. Now remember, the universe is about 14 billion years old. So galaxies started forming in the first 1 million or so years. Their average shape, what they look like. If you're interested in galaxies, then you want to be interested in what they look like. It helps you understand how they got to be the way they are, in the same way that if you're interested in people, studying their features and how those features came about will tell you about their biology and their history. They come in typically two different shapes, and that's spiral and elliptical. And the number of habitable planets, at least one. That is confirmed. Can you guess? Yes, you're living on that planet. But there's probably more, and you're welcome to ask me about that later. So here's some beautiful images of galaxies. Again, this is a beautiful grand design spiral. You can see there are these arms that come out, although they're quite intertwined in this galaxy. You're looking at the light of 1 billion stars here, the integrated light. I've only ever been to a telescope once in my life. You can be an astronomer and not go to telescopes. That's fine. They do make fun of me for that. But the time that I did go, we observed this galaxy. This is called the Sombrero Galaxy. It was astounding. You know, you see, I've seen pictures of this before, but when you actually go yourself and you point an instrument at it and you take the image yourself, it's quite remarkable. So this galaxy is characterized by a disk with a very large halo of many billions of stars. And these stars, they're so small you can't see them individually, but you can see their integrated light as this diffuse halo. What's neat here are these dust lanes. So how do we know that's dust? How do we know what that is? Well, this is the optical light. Hubble is mostly optical. And you can go and look at this at another wavelength. So in this case, we're going to go and look at Sombrero at infrared with the Spitzer Space Telescope, and that's what the Sombrero looks like in the infrared. So let me just blink between the two. So now you have this bright red ring. So what is that? So this is, let's say you're out in the desert, there's a big dust storm. You can't see very far because the light can't propagate without hitting some of that dust. So what happens physically is that dust gets absorbed, the light gets absorbed and gets re-radiated in the infrared. So if you go and look at this galaxy in the infrared, you're seeing the dust that's re-radiating the optical light that the stars behind the dust are putting out. And that's what you see here. And this is one of the amazing things about astronomy. You go and you look at these galaxies at different wavelengths, and it gives you a different piece of the story. So you can look, in this case, between optical and infrared, but also X-ray, gamma ray, ultraviolet, all the different parts of the spectrum and many different ways to observe. All right, so there's Sombrero in the infrared. Galaxies are very dynamic. Over cosmological timescales, over billions of years, they grow and interact. And it's hard to see on this, but these two galaxies are in a dance of colliding together. Here's another one. This is what we would call a major merger, two spiral galaxies colliding together. Here's a group of galaxies merging dynamically. And so I said earlier that galaxies can be spirals or ellipticals, these big round things, flattened disks or big round things. The way to make one of those big round things is to smash together lots of the spirals. The nice ordered orbits of the stars in the galaxy gets disrupted, gets thrown out into random orbits. And what you end up with is something like this. This is a massive elliptical galaxy. Now, one thing I want to show you here, which is quite neat, these things look boring, but you see these here? These are spiral galaxies. So if you want to know the difference between a billion solar mass galaxy and a trillion solar mass galaxy, you're looking at it. Okay? So this is the assembly of galaxies, and hopefully I've given you here a sense of the scale. All right, so let's move on now to supermassive black holes. So we've talked about general relativity, the mathematics that describes black holes, and gravity. We've talked about black holes themselves, how they follow from that, and some of the observational evidence for it. We've talked about galaxies. Okay. So black holes aren't just one solar mass or a few solar masses. They can be up to 1 billion or more times as massive as the sun. And these are supermassive black holes, and they live in the hearts of galaxies. Okay? So how do you find these things? What's the evidence for such insanely exotic objects in our universe? And it's very simple. We can go back to mathematics of the 1600s. So let me show you. Kepler's third law. Kepler showed in 1616, I think, or 1620, somewhere around there, that mass is proportional to the radius cubed divided by the period squared. So what does this mean? This means that if you want to know the mass of the sun, just work out the distance from the Earth to the sun and how long it takes the Earth to do one orbit, the period. And if you can measure those two things, the distance to the sun and how long it takes to go around, then you know the mass of the sun. Okay? Mass is proportional to the radius cubed divided by the period squared. And we can do this for all the planets in the solar system. Here's an example. Here's the orbital period squared in years, years squared. And here's the semi-major axis. It's just the distance, okay, the cube of it, and all the planets sit nicely on this line. It's a very well-defined relationship. So let's apply Kepler's third law to the Milky Way. Okay? A black hole in the Milky Way. Yes or no? So this is the center of the Milky Way. These are the stars right in the center, dead smack. Center of the Milky Way is just down here somewhere, right in the center. And let's point some telescopes at that and follow the orbits of these stars. Because over time, we should be able to see them move. Nothing ever stops. So these stars will be orbiting. And let's track their orbits with the aim of getting how long they take to go around and the radius around the center. So we can apply Kepler's third law. And so astronomers have done this, and here's the result. This star is called S2, and Sagittarius A star is what we're calling the very center of the Milky Way. It's around which S2 orbits, and these are the points. Okay? And you can see it traces an ellipse, so it's not a circle here, it's an ellipse, but most orbits are ellipses. Okay? And it's very well described, and these are the years marked next to it if you're curious. All right? So we have a good measure of the period, how long it takes, and a good measure of the semi-major axis. Okay? But not being satisfied with one star, astronomers measured this for many stars, and you can see here is that star I just showed you, the yellow. But there are many stars here. Now, most of these other stars don't finish their orbit in this time, which is between 1995 and I think 2011. But you can extrapolate fairly well. Okay? So this increases the accuracy of the measurement, because instead of just having one measurement of the center, you have many. And so you can do this and apply Kepler's third law. And yes, the Milky Way has a black hole at its center, and the mass is estimated to be about 2.6 million times the mass of the sun. So nothing else can explain the orbits of these stars. No known physics. Now, you can create some weird physics to try and explain it. But basic Kepler's third law, which describes very beautifully and very accurately our own solar system and many other things, applied to the center of the Milky Way, shows us that in that region of space, there has to be that much mass. Otherwise, these stars would not orbit the way they do, all of them. And if you put that much mass into that volume, just like we saw with Einstein's field equations, you get a region of space-time from which light can't escape, and that's what we call a black hole. So let me show you a picture of the black hole at the center of the Milky Way. Right, there it is. Right, actually, it's not true. Okay, we actually do see black holes, and I'll show you in a minute. Okay, but first, let me make this statement. Every galaxy has a supermassive black hole. Okay, we actually believe this to be true. And I won't go into detail or the evidence for this, but every time we look for one, we find one of some mass. Here's some evidence for that, or at least some examples. These are called quasars, or this is called quasars. Quasars were first discovered. Astronomers thought they were stars. But when you look at the spectrum of it, it doesn't look like a star. I mean, visually, one of these is a star and one of these is a quasar. Can anyone tell the difference, just visually? They're just point-like objects, insanely bright. One of these is at the edge of the observable universe, and the other is in our own galaxy. That's how bright they shine. They're point-like sources that look like stars to the naked eye, but the spectrum reveals that they're not, and they're actually very distant. Okay? This is the quasar, and this is the star. So with Hubble, we can go and image these. All right, here's an example of a quasar for which we couldn't resolve the host galaxy. And here's a more nearby one where the quasar's in the center, but we're able to get imaging of the galaxy itself. So quasars are objects that are very distant and whose light outshines its entire host galaxy. And you either have to catch the quasar when it's fading, or be very lucky, have it very close where you can actually resolve the rest of the galaxy in order to see that they are in galaxies. And this was a point of debate for many decades, what these things were. So we pretty much now know that they result from the collision of gas-rich spiral galaxies. What happens is the gas, the hydrogen gas in those spiral galaxies, from the violence of the collision, gets driven down to where the supermassive black hole is, and gets pushed on. The supermassive black hole starts eating it at an insane rate. As this happens, a disk forms around the black hole, which feeds it. And this disk is so violent, gets so hot, it lights up. And that's what we're seeing. We're not actually seeing the supermassive black hole. We're seeing the accretion disk around it that's lighting up, and lighting up so brightly that it outshines the galaxy itself. And so this image that I showed you before is a good example of something that will end up as a quasar in maybe 500 million years as this collision progresses. We see other examples of this, for example, active radio galaxies. So instead of looking in the optical light, which is where we see quasars, we look in the radio now. Many galaxies show jets coming out of their centers of very fast gas. And these jets are being driven by a central supermassive black hole in an active phase, and here's a picture of one of those. This is M87, a massive elliptical galaxy. These jets tend to be predominantly in these elliptical galaxies, whereas the quasars tend to be predominantly in the spiral galaxies. And again, this gives you some hint about the evolutionary sequence, or the different evolutionary sequences that lead to the different types of active supermassive black holes. And this is a very beautiful image that I found. This is Centaurus A. It's actually a very active supermassive black hole in the center. So this is a combination of many different wavelengths. And so you see the optical and infrared light. Again, there's the disk there in the dust, like we saw before. And what you're seeing here are radio jets. So this is the radio emission pushing out into the interstellar and intergalactic medium from the active supermassive black hole. And if you can see these shells here, you see those? All right? Those shells are the intergalactic gas that you would otherwise not see. It's invisible. But what happens is, as these jets come out, it hits the gas and it shocks it, and the gas starts to fluoresce. And if you look at this region of space at the right wavelength, you see this fluorescence, and that's what you're seeing here. All right? Absolutely astounding. Right, so supermassive black holes at the hearts of galaxies. They're very important, they're real, they're there, we have one in our own galaxy. Okay? Black holes are bizarre objects, predicted first through theory and then confirmed through observation. But there is more theory that theory says about black holes, and so we'll spend the last couple of minutes talking about wormholes. So who here has heard about wormholes? Star Trek fans? Yeah. Right. You know how to build one? Yeah. Do you remember the Star Trek thing? They said, how does the warp drive work? And the creator said, very well, thank you. Right. Okay. There's a lot of things in science fiction which we would love to be true, which are physically impossible. And you can demonstrate they're physically impossible. Wormholes have not been ruled out, and they are a theoretical prediction. You can solve the field equations for a wormhole metric and get a stable answer. Now, there are reasons to believe that, the reasons you might want to believe that that's not going to happen, or you can't do that, and we may still discover consequences and limitations on the equations that prohibit them. But to date, as far as I know, theoretically you can still build a wormhole. But let me just show you why that's actually going to be very difficult from an engineering point of view. All right, so here's our fabric of space-time again. Okay, but this time I've bent the sheet over. Okay, I can just do that. Okay, you'd never notice it. You're not going to feel it. You're stuck on flat land in this two-dimensional universe. Okay, so you don't know about this. And let's put a black hole here at this point. And let's actually walk over around here and put a black hole on this point here. And anything that can be cut can be sewn. And let's, through the magic of some yet undiscovered physics and engineering, sew the two mouths, these two ends, together. And if we do that, we can create a channel through this region of space-time. Okay? So you can use this to traverse parts between 2 points in the universe faster than light can travel between those 2 points. So notice I didn't say you can travel faster than light, because you can't. Special relativity forbids this. And to the extent that it's been tested, which is at an insane level of precision, it's true. But that does not mean that you can't get between 2 points in space faster than light would be able to get between those 2 points. And so let me show you how you do this. Faster than light travel. So here is your wormhole. So this is what we call hyperspace. So we add a dimension outside of our normal space-time dimension so we can visualize it. And I've built a wormhole here by creating two black holes, one here, and joining them together. And here I am on Earth, and here's Vega, and I want to get to Vega. So through the conventional route, I'll have to go all this way here, and that would take 25 light years. That's how long light would take. But with my wormhole, I can get there much faster. I probably wouldn't even need to travel at the speed of light to still beat light. That goes the long way. Okay, so that's one way you can travel faster than light, using a wormhole. Now, if this is true, if you could do this, special relativity tells us that there are far more important consequences than just being able to travel faster than light can travel. And this is time travel. So special relativity tells us that if you have two clocks that are synchronized to some insane level of precision, and then you take one of those clocks and you put it on a jet and you fly it around the world 100 times, and then you bring them back. So you've accelerated one of these clocks relative to the other one, that when you bring them back, they will be out of sync. These are the time dilation effects that we were discussing as you were approaching your black hole, and time from the observer watching you from a distance seemed to slow down. It's the same effects here. So how can you use this to your advantage to create a time machine? So that's pretty easy, actually. If you can do this level of engineering, you can do this, right? Take one of the mouths, which is just a region of space-time, and accelerate it. Now remember, we created this mouth through an insane level of gravitational force, right? Basically putting lots of mass so we can bend space-time to the point where we create a black hole, which we then connect to create the wormhole. So if that's mass there that's bending space-time, we can move it. Let's accelerate it. Let's accelerate it relative to the other mouth, which is the same universe but another region of space-time. And this is when special relativity comes into play. They get out of sync in their time. And if that's the case, you can go in one mouth and you can come out the other mouth before you went in the mouth. All right? So again, engineering problem. But if you can do it and the laws of physics don't forbid it, then it's possible. Okay? So what's a consequence of that? You can go and kill yourself before you go in. So how did you go in? So you could go and kill yourself, so then you could go and kill yourself. Right? So you see the paradoxes which then eventuate from, that naturally flow from these types of situations. So physicists tend to believe that this doesn't happen. This can't happen, right? Because if it did happen, the order in the universe that we understand just wouldn't be. The universe would not be the way it is, right? And it's some undiscovered principle or some yet to be fleshed out theory which clarifies this. So, how do you avoid paradoxes with a wormhole? The thing I didn't touch on, but they're actually very unstable. So you can create the throat, but anything that traverses it has to actually move faster than light to get through before it collapses. So there's a slight problem there as well. Again, this is what I would call an engineering problem, right? Keeping that open. But if engineers can solve that, if physicists tell the engineers that it's not forbidden by the laws of physics, then in theory you could do it, okay? But for these reasons, these are real problems, right, of course. And it's probably why we believe wormholes don't exist and can't see them as you do in science fiction. All right, so let me finish up there. Let me just say that the universe is vast and amazing. I hope I've given you some sense of the wonder that I felt when I was younger and when I started down this journey, and what I still feel as I go into work each morning. Take some time to look at the universe through a telescope and discover it for yourself. Go look at the rings of Saturn. Go look at the moon. Take your kids out. It's an amazing sight. It's your universe. So please go and enjoy it. And let me just finish by saying thank you for coming tonight.
Great. Well, thank you very much for a very interesting talk. And we do have some time for a few questions now. And Damien will be running the microphone around.
Thank you. When we hear about a star collapsing, it always seems to be a violent and apparently very rapid event. I'm just wondering why is it that stars don't slowly burn up their fuel and just collapse in a more controlled way?
So I think the short answer is that it burns its fuel at the most efficient rate, which means it actually very rapidly runs out. It doesn't slowly run out of fuel. It tries its hardest to maintain that balance until it can't. It's like trying to hold something up, and you're holding it, and you're holding it, and at that point it's gone. And at that point, there's nothing to stop the gravity anymore. And there's so much mass, it just happens very, very rapidly from that point on. So the time scales involved for that last part where the fuel runs out are actually very short relative to the rest of the lifetime of the star. That's a great question. The question was, what are the chances of two stars colliding when galaxies collide? Galaxies are actually pretty empty. So the stars might be big and impressive and bright, and the collective light of them makes a galaxy shine from a great distance. But the stars themselves can be approximated as pinpricks. And so stars will only typically ever know about other stars through long-distance gravitational interaction, so they'll come past. But the chance of two stars actually colliding, that those tiny points in space relative to the vastness of a galaxy, is pretty small, and they will almost never collide. More likely, the orbits of the stars will get thrown out. And people have actually run simulations. So at the moment, many people may not know, we're in the early stages of a collision ourselves. The Milky Way and Andromeda is on a collision course, and we can measure the relative velocities, and we can estimate that in about 5 billion years, we will all need to panic, throw our arms up in the air, and run around in circles. What will probably happen, though, is the solar system, will definitely happen, is the solar system will remain intact, because the gravity of the sun for the planets is far stronger than the entire gravitational force of the galaxies going through each other. So on the solar system scale, what's most important for the dynamics of the Earth is the sun. On galactic scales, these things get torn to pieces. The solar system may get flung out with other stars collectively as it all gets torn to pieces. But the chance of two stars running into each other or having that direct collision is very, very small. Okay, you worked it out. Yes, I'll take your word for it. The density would be higher for black holes. So the question was, the density of a neutron star was?
You work it out. 1 times the mass of the sun shrinks to about 20 kilometres in diameter. Work it out.
Hang on, where's my pen?
1 billion tonnes per cubic centimetre.
We'll leave that as an exercise for the audience. But yes, the question is, what's denser, a black hole or a neutron star? And the black hole is definitely denser. Although you can turn a neutron star into a black hole quite easily, actually, and this happens. Do I have? I'm not sure if I have the slide on it. Oh, here it is. Oh, you can't see that. Sorry, just a sec. All right, you can turn a neutron star. So when the supernova happens, not every star ends up as a black hole. Some, more likely, they'll end up as a neutron star. So here's a neutron star. Quite often, stars come in binaries. And if a star does go in binary, one of them goes supernova, ends up as a neutron star. It's a neutron star now orbiting around the other star, which might be a different star and much longer lived. But what can often happen is this neutron star is close enough, and it's still quite an extreme object with very high gravity, but not enough to be a black hole. It starts sucking the mass off the other star as they orbit. So it'll start sucking it off, until it gets to a mass, a critical mass, where it can then turn into a black hole. Okay? And so at that point, a neutron star now becomes dense enough. You get runaway gravitational collapse. The forces that are holding the neutron star up, which are the atomic forces, are no longer enough to stop the runaway collapse.
I'm right in saying, too, therefore, the density of the nucleus of an atom, which is what the nucleus would be at the same density.
It probably is, but let's not go there.
It shows you how spread it is.
Yeah, that's right. Most.
As Rutherford found out.
Well, the reason why my hand doesn't go through this monitor, I mean, most of it's all space. It's because of the electromagnetic forces, not because there's actually something solid there.
Right.
Yeah, it looks solid to our eyes, but yeah.
Hi, I was just wondering, where a supermassive star goes supernova, it explodes, sheds some of its mass,
Yep.
or a lot of its mass, it then becomes a black hole. The black hole must therefore have a lesser mass than the original star that created it. Excuse me, that created it.
Yes, typically, yes.
So in which case, how is a supermassive star or a black hole different? Why should the black hole have such an effect on space-time where a massive star doesn't? Is it density or is it mass that counts?
It's actually, well, it's really density, because you can take the entire solar system. The sun is not a black hole, but if you squashed it down to a small enough volume, it becomes a black hole. So you're right in saying that when stars go supernova, they shed some of their mass. So the black hole will typically be at a lower mass than the original star. Some of that will be thrown off. But if the conditions are right, and you take away that pressure and there's enough initial mass there, you can get runaway collapse, which then can't be stopped by the degenerate pressure of the atoms themselves or any of the other forces of nature. And that's when we get to runaway collapse in a black hole.
Yes, hello. Very good talk. Thank you very much. If we go back to that very first picture where you had the space-time curvature, please, that'll be helpful.
This one?
The next one will be good, yeah. What does it, because I've heard quite a number of times people asking what is the density of something. What does it mean to calculate a density in this context? Because your space-time itself is curved, so whereas when I think of density, I think of a mass in some sort of space-time volume itself. The other question also was perhaps related. In some sense, we can actually get rid of those balls, and the image will still be the same, because in some sense, it's not like though out of space-time there are balls curving things. It's just that we visualize the curvature as resulting from some mass.
So I hope I can answer your question. So
And that might get to the density as well. But anyway, thank you very much.
Your first question was, I guess, related to the previous question about density and volume. What does volume mean in this context? I've, of course, simplified things here to make them understandable. And this is how physicists had to think about it, because these concepts were very foreign initially. And if you some people might know Einstein never got a Nobel Prize for general relativity. It was very controversial, and part of it was that the many physicists of the time found it really hard to get their head around these concepts and accept them as reality. Now, I've grown up in a world where general relativity is taught in university, so they seem okay to me, but back then it was really devastating. So I have simplified things here which then don't often extend to a natural explanation. But the simplest way to think about it from this point of view is just to take a volume of space and just see how much mass you can get into that fixed volume. And if you can get enough mass into that fixed volume, so the more mass you put into that fixed volume, the more curvature you're going to create in the field equations. So the field equations will predict how much curvature you get for a given mass in a fixed volume. And at some point for that volume, if you put enough mass in, the curvature is sufficiently high that light can't get out. So that's one way to think about it. And that comes back to your question about the density, I think. The second part of the question, I'm not sure if I've understood it, if I totally agree. If you take the mass out of this, then there's no curvature. It's flat. So there's no gravity. So it's as simple as that. So this analogy works because we have an otherwise unperturbed space-time, so no curvature, which means no gravity, and then we put some mass in, and we watch what it does to the space-time. What it does is induce curvature.
But that mass is actually in the fabric of space-time, if you follow your first example.
That's right. So I'm in the fabric of space-time. I'm actually bending space-time around me as I walk. Can you see? Right? It's just so small because, my mass is not that much. The Earth has much larger mass, and then we feel its effects. And that effect is curving of space-time. And if you want to see what curving of space-time looks like, I'll throw this at you, and then you can see it, the effect of that.
What are your thoughts on the possibility of white holes?
White holes. I don't know a lot about white holes, to be honest. Maybe you can tell me. What are your thoughts? I mean, as far as I know, white holes are really the other end of a wormhole. So I think they're theoretical objects again. I don't know. Can't answer your question, sorry.
Is a white hole equivalent to what the Big Bang was supposed to be, the other end of it?
No, that Big Bang's separate, although general relativity describes cosmology of our universe at an insane level of precision as well. So.
Yeah, just a question on the clocks you were speaking about before. We synchronize them and then send one round the Earth many times in a jet and come back and find they're out of sync.
Yep.
Given that clocks are generally operated by some kind of mechanism, whether it's a wind-up spring or a battery in a motor or whatever, how is the actual mechanism of the clock affected to change the time?
So it's a good question. So the question was, I said you take two clocks, you synchronize them, you accelerate one relative to the other, bring it back, they're out of sync. They're out of sync exactly by how much special relativity predicts. So that's what I said. And the question was about how does the mechanism of the clock, the way the clock records time, how is that affected by these processes?
Yes,
so what they do is they use atomic clocks.
Atomic clock.
Yeah, so they use basically the decay of cesium atoms, which are unaffected by any of these such effects. It's a nuclear effect, an atomic effect, right? A radioactive decay effect governed by quantum mechanics, which is very accurately described to many, many decimal places. So you can find a timepiece which is unaffected by any dynamical or general relativistic effects. So then you can trust that the synchronization that you've reached, when it gets out of sync, getting out of sync is due to the relativistic effects.
Right, so just an electrically operated clock or a wind-up clock wouldn't be accurate enough to tell you whether it was out of sequence.
Yeah, you would never be able to get a conventional clock at that level of precision. The differences are very small, very small. And that's why we don't notice this. When I say see you later and I run off, we're actually getting out of sync slightly. But we don't notice this because they're so small. It's only when you get close to the speed of light that these effects start to become, and very extreme environments like the extreme gravitational fields around black holes and other neutron stars are another example of this.
Thank you.
So you said that black holes can suck like basically everything. So I was wondering what happens to the matter that gets sucked into a black hole and where does it go?
Ooh, yes, good question. I'm hoping that you will go and do physics for many years and answer that question. The answer is we don't know. We don't actually know. Our theory breaks down. So we have two fundamental theories of the universe. One is quantum mechanics that describes the very small, insanely accurately, like to an insane level of precision. Your phones, almost everything in this modern world can be traced back to some insight from quantum mechanics and some application of that theory. And at the other end, we have general relativity, which governs the very large dynamics, gravity, planets, cosmology, the universe as a whole. And so what you're really asking is, stuff falls into a black hole, which is very well described by general relativity, the theory of the large, and it gets compressed down. And it will get compressed down to a size smaller than an atom, smaller than that, smaller than that, smaller than that, right? And we're now in the quantum world. And these two theories are not compatible. They actually don't work together. And Einstein spent a lot of his later life trying to unify them because they're insanely accurate for the parts of the world that they describe independently. But they don't unify nicely. And so the answer is we don't know. There will be some unified field theory, some unified quantum theory of gravity or something like that, which then accurately describes. And then we'll say, well, something passes the event horizon, but now a different theory takes over and now explains what actually happens there. And it won't be what general relativity predicts, because general relativity in those regimes is an extension that's probably wrong. It won't be quantum mechanics, because again, quantum mechanics breaks down in those regimes. So that's for future work. That's the future. Hypothetically, what would happen if two stars did collide? Well, I don't think we would need to be hypothetical here. We could probably picture it in our heads. That, well, to be honest, when two black holes collide, it's something similar, except you're colliding black holes, not stars. The mass, the final collision would be twice the mass, or the sum of the two masses. The mass of each star would probably be torn up and thrown out. But the gravitational field of those two stars, I'm guessing, would be much stronger than the force that the mass could be thrown out at. So even though it gets thrown out initially, it will come back very quickly. It will probably come back in the same state because stars are mostly hydrogen, and throwing the mass out, I mean, hydrogen is hydrogen. So you would just end up with a bigger star at the end. Now, then you would need to look at the stellar evolution of stars of that larger mass to see. It probably would have a much shorter lifetime now. Bigger stars tend to burn through their fuel faster and so on, so stellar evolution would be different. So it would be very violent initially, but it would probably settle down quite quickly, just because these things are quite massive.
Time for just a couple more questions.
Is it highly probable that there's other black holes in our solar system?
The question was,
in our Milky Way?
is it highly probable that there are other black holes in our Milky Way? I would say yes, definitely. More than likely. I mean, they're not uncommon. Like I said, we see supermassive black holes at every galaxy that we measure. So why not for stellar mass black holes? And you can make predictions about what you should expect to see this. The challenge is what you should expect to find. The challenge is finding them, because you'll only find black holes one of two ways. One is through their dynamics. So in the center of our galaxy, we only see the black hole because of the dynamics of the stars around it. And the other one is when black holes start eating mass around it. So it has to be close to something that it can steal its mass of. And then you get a disk that lights up because of the violence of the accretion onto the black hole. And they're quasars, for example. So seeing black holes are just floating out there in space where none of these effects are readily observable is difficult. You won't see them.
Thank you. And the final question from the back.
Some black holes shoot off jets, you mentioned earlier.
Yep.
How is it that that jet is able to escape that black hole where nothing else can?
So it's a great question. I had this misconception for a long time, and I was an astronomer, or an astronomy student. I should have known better at that point and then learned. So it's not the black hole that you're seeing, and it's not the jet escaping from the black hole. It's the effects of the disk around the black hole that is feeding it, from which you see this emission. So imagine the black hole, and then you have a jet which would extend out a long way, maybe kilometers away from the black hole on this relative scale. And that jet is in the vicinity of an insanely strong gravitational field, which is the black hole. You get tidal forces as the matter moves in, is sucked in, tidal forces. So the different layers of the disk of matter that's coming in will rub against and heat up. And as it heats up, it lights up. And that light is not close enough. It's not inside the event horizon, so it can escape. This escaping for these objects tends to be directional. Right? And it's to do with magnetic fields and other properties in the vicinity of the black hole. And so that's where it comes out as a jet. Whereas quasars are a different object, different kind of physics going on for the same black holes. Mergers, things aren't so directional. They just light up in all directions in the optical. But these jets are radio, and they come out directionally. So they don't come from the black hole itself. They come from the disk around the black hole. But relative to the galaxy, these scales are tiny anyway. So they look like they come from the center.
So it's been a pleasure. Hopefully you enjoyed it. We had this very interesting talk today. And as a token of our gratitude, it's not an umbrella. Great. So thank you all very much for coming out, and have a pleasant evening.